Welcome to the session on wind load generation for building structures as per the IS 875 code. In this video, we'll talk about the various parameters for wind load generation as per the Indian code and how the same has been implemented in STAAD.Pro. In STAAD.Pro, we have implemented two methods to calculate the wind loads. Method 1 is using the create wind definition option and method 2 is the wind load generator option. In the first method, wind pressure at various heights is calculated first and then the pressure is converted into loads and distributed to the structure. So it's a two-step process. In the second method, wind pressure calculation and distribution is done simultaneously. In both these methods, wind pressure at various heights are calculated. So now let's see how to calculate the wind pressure at various heights as per the IS 875 Part 3 code. First step here is to calculate the design wind speed. Design wind speed depends on various factors like geographical basic wind speed, risk level, terrain roughness and height of structure, local topography, and importance factor for the cyclonic region. To cater for all these, certain factors are defined by the code as K1, K2, K3 and K4. So the design wind speed at a given height will be calculated as Vz is equal to Vb into K1 into K2 into K3 into K4, where Vb is the basic wind speed. Figure 1 of the code shows the various wind speed zones of the country, which is applicable to 10-meter height above mean ground level. Here you can see that the country has 6 wind speed zones, each with a distinct wind speed. Annex A of the code also gives the basic wind speed for some important cities. Next step is to find the value of K factors. Here K1 is the probability factor, the values for which are given in table 1 of the code for different class of structures in different wind zones. For general buildings, K1 value can be taken as 1. For other type of buildings, the values can be taken as shown in the table. Now the value of K2 depends on the height and category of terrain. Terrains are categorized into 4 depending upon the effect of obstructions. Here you can see the 4 categories. Category 1 is open terrain with few or no obstructions and the average height of surrounding object is less than 1.5 meter. Open sea coast or flat plains with no trees comes under this category. Category 2 will have scattered obstructions with heights between 1.5 meter to 10 meter. And category 3 is a terrain with numerous closely spaced obstructions with building size up to 10 meter. Normally towns and industrial areas fall under this category. Category 4 will have numerous large, high closely spaced obstructions. Large city centers or well-developed industrial complexes fall under this category. K2 values are given at 5 meter intervals here. Any value in between can be linearly interpolated. Also note that the higher the height of the terrain, higher will be the K2 factors. K3 caters for the local topographic features such as hills, valleys, cliffs, etc. The value can be taken as 1 in general cases. K4 takes care of the effect of cyclones. To cater for increase in wind speed during cyclones, this factor is used. Here you can see the values used for K4 factor. For important structures such as cyclonic shelters, hospitals, schools, etc., the value is taken as 1.3. For industrial structures, it is 1.15, and for all other structures, the values can be taken as 1. Now that we saw how to calculate the design wind speed, let's go to STAAD.Pro and see how to enter these parameters in the STAAD interface. Here I have a very simple building model. Now to generate wind loads for this structure, let's move to the loading tab. So here at the ribbon menu, you can see two options for wind. One is under the defined and another is the wind load generator. Let's look at the first option, that is the define wind load. The same option is also available under the definitions on the right hand side. Now I want to generate the wind load along the x direction at the windward face of the structure. So let's select the wind option here, and for type 1 I'll be creating a wind along the x direction for the windward face of the building. So I'll enter the command as windward x, and for the code I'll select the Indian code. We have few other codes also available, but I'll be selecting the Indian code for this session. And for type 2, the vendor is acting along the positive x direction, but this time it will be acting at the leeward face. So I'll enter the command as leeward x, and for the third case I will say sideward x. Similarly, you can create wind in the z directions as well. I'm not doing it at the moment. Before we start adding the parameters here, let's have a look at the building dimensions. So let's go to the utilities here and node tools and node to node distance. So this is my length of the building, 22.86, width of the building, and then the height of the building. So now I have the dimensions. So at this point I'll go to the wind definitions and will populate each of these types. So let's select the first option here, the windward face, and say add. And here the code has already been selected by the program. Here you also have an option to enter the height versus intensity values in here. So if you do not want to use the load generator in STAAD.Pro, you can directly enter the values here. Otherwise, you can click on generate and enter the parameters and let the program compute the height versus intensity table for you. So for this session, I'll click on generate, and the IS 875 wind load generator is available for us now. So we have 3 pages, in each of which we'll be entering a few parameters. So first one, the year of publication, it's 2015. And for structure type, we have rectangular clad building option, unclad buildings, and hoardings and lattice tower. So for this exercise, I'll be going ahead with rectangular clad buildings. And the maximum height of the building is already captured by the program. And the ground level elevation is set as 0. Basic wind speed corresponding to all the major cities are available here. So you can select the required city from here, and the corresponding basic wind speed will be captured by the program. You also have an option to use a custom value here. Now comes the K1 factor. For that, you can select the class of structure from this drop down. You have general buildings, temporary buildings, low hazard buildings, etc. So based on, you can select the option from here, and based on which the K1 factors will be chosen by the program. And to calculate the K2 factors, you need to select the terrain category here. So select the required terrain category, and based on the terrain category and height of your terrain, the program will calculate the K2 factors. By default, the interval is kept as 5 meter. That is what the code also gives you. But if you want to change the interval here, you have the option to do so, and the program will give you all the values at 2.5 meter intervals. So any value in between is linearly interpolated by the program. Now you have an option to enter the K3 factors, and also for K4 factor you can select the required structure based on which the program will fetch the K4 values. Now that we have the VB values, K and all the K factors, the program will calculate the design wind speed as VB into K1 into K2 into K3 into K4, and it will be reported as shown in this table. Also, there is a height versus velocity graph plotted by the program. So this is all about the first page where we calculate the design wind speed. Coming to the second page, here we will specify the direction along which we will be applying the wind, and also will enter all the building dimensions, and we also have the option to enter a pressure or force coefficient. Here you can notice that we have 4 directions to use: positive x, negative x, positive z and negative z directions. Also you can see the various phases. So when wind is acting along the positive x direction, A will be your windward phase, B will be the leeward phase, and C and D will be the side phases. Also the dimensions. Length along LX is shown as 18.2888. So in this case, this will be your width, and length along Z, that is the LZ value, which will be your length, and we also have a height parameter here. So all these values are already captured by the program. Now you have the option to enter a pressure or force coefficient. So let's select the pressure coefficient option here. Let's go back to our presentation and see how the pressure coefficients will be calculated by the program. Wind load on a member or a point is calculated as per clause 7.3.1 as F is equal to CPE minus CPI into A into PD, where CP is the external pressure coefficient and CPI is the internal pressure coefficient. These pressure coefficients are applicable to structural elements like walls, roofs and claddings. Code recommends to take the pressure difference between opposite sides of a face of a wall or an element. Hence the term CPE minus CPI is used. Here A is the surface area of the structural element considered, and PD is the design wind pressure. Calculation of PD will be explained later in the session. I'll be looking at the calculation of pressure coefficients for walls in this session. Table 5 of the code gives the external pressure coefficients for various building height and building plan ratios. For the structure that we have considered, H by W ratio comes to be 1.01, which falls in the second category here, and L by W or the building plan ratio comes to be 1.25. So that is what I have shown here. And corresponding to a 0-degree wind angle which is acting on face A, the pressure coefficients will be taken as 0.7. And for phase B or the leeward phase, the value will be minus 0.25. And for the side faces like the faces C and D, the value will be minus 0.6. So since we are considering the pressure coefficients for phase A, we will be considering this 0.7 value at the moment. You can also notice that we have positive as well as negative values here for the pressure coefficients. Here positive value means the wind is acting towards the wall, and the negative means the wind is acting away from the wall as shown here. Now that we have the external pressure coefficients, let's find out the value of internal pressure coefficients to be used for the walls. Internal pressure values depends upon the degree of permeability of cladding to the flow of air. As per clause 7.3.2, in case of buildings where openings are not more than 5% of the wall area, the internal pressure has to be taken as positive and negative 0.2. Buildings with medium openings between with an openings between 5 to 20% of wall area has to be checked for an internal pressure coefficient of 0.5 and negative 0.5. Buildings with openings larger than 20% has to be checked for an internal pressure coefficient of 0.7 and negative 0.7. Here also the positive internal pressure means the pressure is acting towards the wall, and the negative internal pressure means the pressure is acting away from the wall. So these values has to be algebraically added with external pressure coefficients, and whichever causes the higher distress has to be taken for the design. Now let's take a look at the STAAD.Pro GI for this implementation. So let's select the pressure coefficient option here, and pressure coefficients as per clause 7.3.2 and 7.3.3. So the wind on phase A. So if you select the phase A, which is our windward phase, the value of external pressure coefficient is 0.7. You can see that the H by W ratio as well as L by W ratio has been calculated by the program, and you can also check the values of other phases as well, like phase B or phase C and phase D. So the corresponding values will be fetched by the program. You also have an option to enter a custom value for external pressure coefficient. We also have the option for internal pressure coefficient, that is the CPI. So I'll select that option as well. So I'll assume that my building has an opening less than 5%. So the corresponding value, which is 0.2, has been fetched by the program. And the CP net is calculated as CPE minus CPI. So my CPE value here is 0.7 and CPI value is 0.2. So the net pressure will be 0.7 minus 0.2, which will be 0.5. I also have an option to use a negative internal pressure. So if I were to use this one, the net pressure coefficient will be 0.7 minus 0.2, and that will be 0.9. So ideally when you are creating the load types, you can create load types with a positive CPI as well as with a negative CPI, and whichever causes the higher distress, you have to use that particular load for design. Here you also have an option to enter the force coefficient. Currently STAAD.Pro is not calculating the force coefficient, but if you can enter the value of force coefficient as per clause 7.4.2 and enter the values here. Now let's move to the last page in STAAD.Pro. Here we calculate the design wind pressure as PD is equal to KD into KA into KC into PZ, where PZ is equal to 0.6 VZ square. We have already calculated VZ in the first page for various heights. Here KD is the wind directionality factor. This is to cater for the randomness in the direction of wind. Normally for buildings, towers, signs, etc., the value is taken as 0.9, and for circular or near circular structures, the value is taken as 1, since the direction does not matter for such shapes. Ka is the area averaging factor, which can be taken from table 4 of the code. And lastly, the combination factor, which is a reduction factor, whose value has to be taken as 0.9 as per clause 7.3.3.13. So let's enter the values here. And the program now calculates a height versus PZ values first. So PZ will be calculated as 0.6 VZ square, and then the design pressure will be calculated as KD into KA into KZ into PZ, and finally this will be multiplied with the net pressure coefficient CP net, and we get the final intensity here. So with that, I'll say OK. So now we have the height versus intensity table here up to 18.572 meter, which is our building height. Now let's add it here and close. Similarly, you can enter the type 2 wind. Here the only difference that I'll be making is by selecting the face B. So this will be my leeward face, and I'll generate the wind for type 2 case. The same will be done for the type 3 case as well. This time I'll select face C, which is my side face. So this is the first step in wind load generation as per method 1. Now the next step is to apply this pressure to a building. So let's create a few load cases here. I'll select the wind. So this will be my wind along the positive X direction. Wind in the negative X direction. Similarly, you can create wind in the positive and negative Z directions. Since I have not defined my wind in the Z directions, I am not creating the load cases as well. So let's populate the wind along the positive X direction here. Select the wind, and you can see that we have 3 wind type defined. The first one is acting on the windward face, second on the leeward face, and third on the side faces. So for the first case, I'll be applying my wind on the windward face. So the exposed surface will be X, which is my windward face, and I'll be entering a factor of 1, meaning it is applied along the positive X direction or positive direction. So program can identify the faces correctly in most of the cases, but when the structure geometry becomes complex, program might need our help to identify the faces correctly. In such cases, we can specify the X, Y, Z ranges for the program to correctly identify the faces. So this is similar to the function that we have in floor load generation in STAAD.Pro. Since our geometry is simple, I'll ignore at this moment, but I'll show you this feature also. Here we have another option where we can define the type of our structure, like whether it is open structure or a closed structure. By default, the program assumes that the structure is closed. You can select this option to make it an open structure. I'll explain the difference between the two in a minute. So this is the wind that I have just added. So now you can see that now the wind is acting along the positive X direction, and which is acting at the windward face of the building. You can see the arrow marks representing the wind loads, and the tributary area is marked as hashed areas. So now let's see how the program calculated these tributary areas and how it has distributed these pressures onto these nodes. So let's go back to our presentation first. So let's first discuss the difference between a closed and open structure. A closed structure is one which do not let wind to blow through them. The members on the exposed face is called panels for a closed structure. An open structure is one which allows wind to blow through them. Here the wind is directly acted on the members. In a closed structure, wind load is applied on the nodes, whereas in an open structure it is applied on the members. So the method of load distribution in both these cases will be discussed in the coming slides. Normally commercial and residential buildings comes under the closed structure category, and transmission or communication towers comes under the open structure category. Now let's see how STAAD identifies the closed panels and distribute the load. For STAAD.Pro, the members has to form a closed panel for correct load distribution, and the panel should be formed by frame members. That means plate or solid elements will not be considered as an edge of the panel. Also, if one side is bound by support, it will be considered as a closed panel. So, in this case, panel 1, 2, 3, etc. are closed because they have supports on one side. Panel 4, 5 and 6 are also closed because they have frame members on all four sides. Panel 7, 8 and 9 are incomplete since the fourth edge is open here. Once a program identifies a closed panel, it has to find a tributary area to distribute the pressure. So let's see how to do that. Here is a closed panel with 6 sides, and we have node numbers 1 to 6 for which we need to find the tributary areas. So the first step in here is to find the CG of the panel. So first find the CG. Now draw straight lines from the CG to the midpoint of the members that form the panel boundary. Midpoint CG to the midpoint. Now we get several quadrilaterals. So the area contained in any quadrilateral is allocated as the influence area for the node located at the meeting point of the two members. So for node 1, this is the influence area, and for node 2, this will be the influence area, and so on. For an open structure, the wind is directly applied on the structure. Here the load intensity will be based on the individual dimensions of the member. So here the program determines the width of the individual members and is multiplied by the wind pressure and is distributed as the UDL for the member. Please note that for open structure, all the members in the structure will be receiving the load, except for the members whose local x-axis is parallel to the direction of wind. Now let's go back to STAAD.Pro and apply the wind in the leeward and side faces. Here I'll continue with the wind in the positive x direction itself. Within that, I'll add wind for the leeward face and side faces. So let's select the wind load 3, and this time I want to apply the wind on the leeward face. So I'll select the wind type 2, and here I have to apply it on the leeward face. So I'll select the leeward face option here, and I'll say add. You can see it has been applied on the leeward faces, and for the side faces my load type will be 3, and here I'll select the Z option, which is the sideboard face. So I'll select this Z here, and this time I am applying the wind on the right side face. So I'll use a factor of 1 and say add, and now it is applied on the right side face. And to apply it on the left side face, I'll use a factor of -1. You can refer to this loading convention figures here and understand how the positive and negative factors has been applied. So with that, I'll say add, and now I have the wind applied on the left side face as well. Let's also look at the winds along the negative x direction once. So here let's say add and wind load. So this time I want to apply the wind in the negative x direction. So I'll use a factor of -1 here, and now it will be applied in this phase. And let's also show you how this ranges work. So let's say I only want to apply the wind from 10 meter to 18.572 meter. So I'll just enter value of 9.9 here, and this one I'll enter value of 18.6. Always make sure to have some tolerances when you enter the ranges here. So in this case, instead of 10, I have entered a value of 9.9, and instead of 18.5, I have entered a value of 18.6. So let's click on add, and you can see here the wind is now only applied from 10 meter to the panels which is within 10 meter and 18.6 meter. So this is how you can use the ranges option in STAAD.Pro. Similarly, for wind along the negative x direction, you can apply the load on the side faces as well as for the leeward faces. So this is the first method of wind load generation, where you define the wind types first and then distribute that wind intensity on the structure using the load cases. Now let's move on to the next method, where both these steps will be combined. So let's use another file for that one. So the second method is the wind load generator option. This option is currently implemented for the Indian code only. So let's select the IS 875 from here. In the first page, we'll be entering all the data to calculate the design wind pressure. So this method is mostly suited for rectangular clad buildings and unclad frame buildings. So if you were to apply wind on a tower structure, you can use the first method that we have discussed. This method is mostly used for the building structures. Here the maximum height is captured by the program, and the ground elevation is set as 0 meter. You also have to specify the load case number here. Since the program is generating the load cases, I already have a dead load and live load case in my model. So the wind load will be starting with load case number 3. You can also use a custom option here and define the custom load case number. Now to calculate the design wind speed, we'll enter the basic wind speed based on the city that we select. And K1 factor can be fetched by selecting the class of structure from here, and topography factor can be directly entered. For K4 or the cyclonic factor, you can select the type of the structure based on which the program will fetch the K4 values. For calculating the K2 factor, you can select the terrain category from here, and the program will fetch the corresponding K2 factors. And you also can enter the KD, KA and KC factors here. Now that we have all the K factors and the design wind speed, the program will calculate the design wind pressure as discussed earlier. And in the second page, here the program has already fetched the building dimensions, and you can notice here that we do not have to specify any specific wind load direction. By default, the program will be calculating the wind in all the directions: wind in positive x direction, wind in negative x direction, and in positive and negative z directions. Here also you can notice the building faces, the windward face, leeward face, and the side faces. Now we have the option for pressure as well as force coefficients. Let's go ahead with the pressure coefficients. Here the program has already fetched the external pressure coefficient values from the code for all the directions and for all the faces. You also have an option to enter the internal pressure coefficients. It is selected by default, and you can select the corresponding option from here. And there is an option also to use a negative CPI. The program will create additional load cases corresponding to these negative internal pressures. For force coefficients, you can select the force coefficient option here and enter the corresponding values in here. Now comes the part where we need to define the faces. Program identifies the faces by default, and you can see the member numbers here for the faces that the program has identified. But since our building has a sloped roof, there is a chance that the load will not be applied correctly. So for rectangular buildings with flat roof, you can go ahead with the faces identified by the program. For the type of building that I have selected here, I will select my faces using the group option, or I have the member list or the range options. In here I have already created 4 groups using the create group option in STAAD.Pro. So I'll use that option, and here I'll select the corresponding faces. So face A, face B, face C, and face D. Please note that these are all the faces that I have created previously in my model, and I have used the beam grouping option. So if it is face A, I have selected the members or the beams and columns in face A and created a group, and similarly for face B, I have selected all the members in the face B, and similarly for face C and D. You also have an option to exclude any of the faces if needed. So with this, I can click on generate. Here you can see that program has generated 4 load types: wind along the positive x direction, along the negative direction, and wind along the positive z and negative z directions. And it has also generated a few load cases. Load cases 3 to 10 has been generated by the program. So the first load case is wind along the positive x direction with a positive internal pressure, and in here we have wind acting on the windward face, leeward face and side faces. The next one is wind along the positive x direction but with a negative internal pressure. Similarly, we have wind along the negative x directions with positive and negative internal pressure, and the wind along the positive and negative z with positive and negative internal pressures. So all these load cases are generated by the program with the parameters that you have provided. So I would call this as an automatic wind load generator for building structures for the Indian code. Now we also have roof for this structure. So currently there is no option to generate wind loads for the roof structures. So you can manually calculate the wind on the roof and apply this on the structure. So to conclude, there are 2 methods implemented in STAAD.Pro for wind load generation as per the Indian code. One is using the define option and another using the wind load generator. Wind load generator is suited for cladded and unclad buildings, and for all the other general structures you can use the define wind load option. Also note that these features are implemented in STAAD.Pro Connect Edition update 8 or higher. So if you are using any other previous versions, please upgrade to the latest and try these options. Thank you.